Thank you very much. Thank you very much, Anand. Thank you very much, everyone, Harsha, for the invitation. It's a real honor and a pleasure to be here discussing with you. During these lectures, I thought of talking about something that has interested me since the beginning of my academic career, but I'll give different flavors to it every day. Unless you get tired of it, then I can improvise and do something else. I'm really going to go old school. I'm going to talk about ray optics, the most primitive description of light, which I think we should not put aside just yet. There's a lot of insights that it gives us that we don't get with more precise models of the behavior of light. So the slides that you see here, I'm just going to use as an aid. I will be using the board as well. These slides I prepared for an event 2 years ago, right before the pandemic, to commemorate the 200 years of the wave theory of Fresnel. So there was a special symposium, and my talk was on this. Well, the title, I had to show them first this version of the title, but then I told them I speak much faster in English, and you only gave me 15 minutes, so I went with this. So one of the things that are coming, the things that interest me of this connection is all the intuition that you get from the ray model. The fact that if you use the ray model well, you can actually understand very well wave aspects that you wouldn't think you could. But also that the same mathematical connection between rays and waves, to a large degree, is the mathematical connection between classical mechanics and quantum mechanics. So by learning about this connection, we're also learning about the corresponding connection of classical and quantum mechanics. So I guess just like quantum mechanics has surpassed classical mechanics, but we don't use quantum mechanics for everything. We still design bridges using classical mechanics. We still use geometrical optics for many, many things. So what I want to discuss is, given that there's this new way, new, 200 years old, way of thinking of light as waves, how does this older framework fit in it? What is the meaning of a ray in the wave theory? So in the old days, rays were thought to be physics, the physical truth. Maybe they were, these rays meant paths that are the paths of little particles of light, whatever these are, that are perfectly localized, that you can specify their direction and their position without a problem. And the main behavior of rays is very simple. So in many countries, we associate this with Snell's law. Of course, I've learned working in France that Snell's law is not called Snell's law there. It's called the law of Descartes. Yeah, some nationalism. But neither of them were the first, of course. Even in Europe, Harriot was much earlier than them. And Ibn Zahel proposed this law many hundreds of years before any of them. So this just tells you that rays travel in a straight line, but they bend when the refractive index changes. And there's a simple law for how this changes. And I guess I should make a first note here, which is, so ray optics comes in 3 flavors. There's 3 ways to think about, at least 3 ways of thinking about ray optics. So I mentioned one, which is Snell's law. Or more generally, I could say ray tracing. This is what the software we buy, CMAX, etc., does. It knows how, if it follows a ray and knows how it bends, etc. But there's another way of thinking of rays, which is related to the last guy on my slide, which is Fermat's theory. that tells me that if I know the initial point and the final point, the path that the ray will follow to get from one to the other is the path that takes the shortest time, or it's a path that is extremal in optical path length. And this one, it feels very different from local laws of tracing things. It's easy enough to show that they're equivalent, but it does feel different. And this is an example of a case where you can formulate a simple law in a way that gives some intuition, but also seems a bit magical. I mean, you say, from here to here, the ray knows somehow how it will get there in the fastest possible way. That seems a bit metaphysical. It's like, how does the ray know these things? But of course, you can show that this is equivalent to this, and there's nothing surprising about this. The ray locally decides what to do based on what it encounters at each point. So it's just a different formulation. And there's a third one, which is called the iconal equation. And this is more recent. So the first person who formulated something like this was Hamilton, and then another person, Bruns, who used the name iconal, and for some reason that name stuck. Hamilton's characteristic function is the same thing, even a bit more sophisticated version of the same thing. So here the key equation is, the key quantity is something that's called the iconal. It's a function of position and satisfies a simple law, well, simple to write, but not so simple to solve. The gradient of this dot itself, so modulus square, is equal to the refractive index as a function of position squared. So this is another way to introduce geometrical optics. It doesn't look like it, but all of geometrical optics is there. You can derive everything from here. And if you're interested and we have time, I can go from this to, for example, this path, this one. So it's a matter of parametrizing this solution using something called the method of characteristics. And you can get to the ray tracing equations from this equation. But I say this so we're ready to see that there are many ways to connect rays and waves, and they will naturally connect to different of these different ways of thinking about it. So if you have any question at any point, just don't hesitate. Let me know. Okay, very good. So as I said, in free space, rays travel on straight lines, and looking at scenes like this, you can understand why they came up with the ray model. I mean, you see the sun, you see the light clearly is going on straight lines. I mean, it's obvious, you would say. Yes?
Regarding this connection,
yeah.
the Fermat's theorem is largely a time implementation of minimization.
Yeah.
Sort of.
Yeah.
Whereas the iconal is completely spatial.
Yes, yes. Well, it's...
They seem to be connected.
Yeah. So you can think of Fermat's as temporal, but you can state it in a spatial way. If you define the optical path length, then as a quantity you minimize. It just happens that is proportional to the speed, and therefore you can connect it to time. So this is, for example, a description of a focus wave with some aberrations, and I'm going to be using this picture later to give some intuition. So everything was well until just a bit over 200 years ago. First with Young, and then with people like Arago and Fresnel. And then these guys came in and took over. So the waves came and superseded the previous theory. Now this is an irrelevant point, but something that amused me. I swear that I got these images from the internet. All the ray people look to your left. And all the wave people look to your right. I did not change that. once we understood that light is waves, then a lot of phenomena like interference, like birefringence, a lot of things made sense. Took some convincing, and there's some wonderful stories involving Arago of the fights between the ray and wave people. Poisson was a big defender of ray theory, and there were some. This was turbulent time politically in France. It's always a turbulent time politically in France, but this was one of them, and these two guys were on opposite sides of the spectrum. Fresnel was the protégé of Arago, and Fresnel got into political trouble also because of his ideas. He was on house arrest, and that's when he did all his experiments. So it's like lockdown. It's if you happen to have your experimental setup at home, it's fine. Well, I'll tell you about Arago. Like, it's one of my newfound heroes. He's amazing. So the idea is then to think of how to reconcile this picture of a focused beam with rays. And maybe before discussing that, let me motivate this with some questions, particularly for the students, but not only for the students. Anyone can answer. So think of a simpler focused beam that this has some aberrations. Let's just think of a Gaussian beam, paraxial Gaussian beam. So the standard picture that we draw on the board is something like this. So the beam comes like this. It's particularly intense here. The wavefronts are curved this way here. They're curved this way here. So what is the definition of a ray within wave theory? Anyone? How would you define a ray? Anand.
Bunch of rays?
Sorry?
I can't do it with one ray. Bunch of rays.
Yeah. So you think of the wavefronts, and the rays are what? Perpendicular to the wavefronts. Okay, so we have rays going like this. What happens to these wavefronts when we get close to the waist? So the wavefronts, how's the wavefront here? Flat. So the wavefronts for a Gaussian beam actually they curve like this. They have some maximum curvature at some point, and then they start become like a spherical wave. And same thing on this direction. So like this. So if I believe you, and I think that if I believe Anand, and I think that a ray is perpendicular to the wavefronts, I come like this, and then this would do something like that. And this ray here would come here, and would do something like that. This ray would come here and would do something like that. Are these the rays that we know? No, they're bending. They're not going on a straight line. I was told they always went on a straight line in free space. So rays are not exactly normal to the wavefronts. That's, and I'll talk about what is normal to the wavefronts and why this happens. So that is intriguing. So one of these things that we hear a lot, rays are the normal to the wavefronts. That's only approximately true if you're very far from a focal region, or a region of strong interference. If the amplitude varies slowly, yeah, that's approximately true. But it is not strictly true, and it's definitely not true here. So it is not evident what rays are in this framework, and that's what I want to discuss today. So one other thing that was like a nail in the coffin of simplistic ray theory as the explanation of physics is the Arago spot or Poisson spot. So some people know it as the Poisson spot because Poisson, to prove that wave theory was ridiculous, said, if you have an obstacle that is perfectly circular and you look at the shadow, you'll see a bright spot at the center. It's as bright as a field would be if the obstacle were not there. So that is obviously wrong, so your theory is not correct. And Arago say, yeah, I'll show you, and he did the experiment and found the spot. So some people call it the Poisson spot, with merit, because Poisson figured out that this should be there, even though he didn't believe in it, or Arago that actually found it. So this is one aspect that if I have the time, I'll talk about this in terms of rays. Even this can be explained in terms of rays. So rays are not dead. We just have to think about them differently. Okay, I'll skip that. So this is the question I want to answer. Do rays still tell us something useful about waves? So before coming to address this picture, let me come back here. And think of how we can get rays from waves. So I'm going to start from this equation. Sorry, this was prepared for French people who use this symbol for the Laplacian. So let me transcribe this. Teaching in France is very interesting. Yeah. I hope my French students don't see this video. So, what is this equation? Helmholtz equation. How do I get it? Yeah, you start with Maxwell's equations, you take the curl of the third, you simplify, you go to the monochromatic case, and then you ignore vector, the vector character of light to make life simpler, and you get to something like this. So many of the ways to connect rays and waves can be thought of as ansatz for u. So you say my field as a function of position is something. What is the more natural way to break this complex field, you would think? So what we usually do, which has some intuition in optics, is to say, well, it has an amplitude, and it has a phase. And I put a k, where k, well, I keep assuming that everyone here is an optics person. K is the pi over lambda. Is the wave number. Is typically large because lambda is small compared to regular scale. Well, sometimes it's large, or sometimes it's not. But let's assume that this is a large quantity. So then I'm going to take this and just throw it in there. Should I do it in real time, or should I just jump to the result? And is it I can do it quickly, but okay. So what is the gradient of this? Well, it's the gradient of the amplitude. So it's when the gradient applies to the amplitude, but not to the phase. And then there's another term where the amplitude stays the same, but we apply it to the phase term. So I have an ik amplitude times the gradient of the phase. All that times the exponential. Now if I take the Laplacian, is the divergence of this. So I have to apply another nabla dot this. So there's a term where this hits this. So I have the Laplacian of the amplitude. Then I have a term where then I have a few terms proportional to ik. One where the second nabla hits A. So I have nabla A dot nabla phi plus when the second nabla hits this, so A Laplacian of phi. And then when the nabla hits the exponential, that gives me another, there's a combination with this one, and this gives me another one of these terms. So I put a 2 here. And then when that is combined with this, I have 2 times ik, so I have minus k squared a nabla phi dot nabla phi, so I can write as this. So if I substitute this into the equation, I get that 0 is equal to, and I'm going to separate this into powers of k. So I have, or rather, I'm going to break it into real and imaginary parts, so k squared. I'm going to factor that, so I have n squared minus nabla squared times a. So that's this one and this one, but then I have this one plus nabla square a divided by k squared. That's the real part, then plus the imaginary part, which is these terms. It's only this one and this one. And I'm going to play, sorry. This parentheses I close here, sorry. If I multiply these two terms by a and divide by a, I have 2a gradient of a, which is the same as gradient of a squared. And then I have a squared, and then I have 2 gradient of a squared dot gradient of phi plus a divergence of gradient of phi, and that I can write as 1 over a, the divergence of a squared into phi. Okay, we're all good? Okay, let's see if I got it right. So I substitute this, and we get 2 equations. I can solve for this one. So if something is 0, and it's a complex quantity, the real part has to be 0, the imaginary part has to be 0. This one here tells me that if I call this S arrow, this is essentially the pointing vector for a scalar field, is the flux density. And it's telling me the flux density has 0 divergence because there are no sources or sinks, and we're in the stationary case. So this is conservation of power. This one here is interesting because I can write exactly in this way. Does it remind you of someone? The icon. Looks a lot like the icon. What is the difference between the iconal and this? Is this term. When can I ignore this term? Well, this term with nabla squared. So I can ignore it if this gradient is very small. If the rate of change of A is small compared to in the scale of the wavelength, if k squared is much bigger. So in that case, this goes away, and I have the iconal. And that explains why these look like rays to me away from this region. In this region, the amplitude is smooth, and therefore its second derivative is small. And this I can neglect. But near the focus is this changes quickly. And that means that I can no longer forget this term. I mentioned before that I can solve this equation, this type of equation, by parametrizing it. Well, I can do the same thing with this. It just turns really difficult to trace. But what this does is cause an extra deviation of the rays. This is the term responsible for the rays bending here. Rays repel each other. Well, not rays. These lines that I'm going to call flux lines, I can call them flux lines because this is the flux. This is the lines followed by this flux. This is proportional to the gradient of the phase. Therefore, these are normal to the wavefronts. So these are the paths of normal to the wavefronts that are bending. So this bending happens because of that term. So there are many reflections that one can make here. One is the analogy with quantum mechanics. I started from Helmholtz equation. I could do the same thing with Schrödinger's equation, where I think of time as z, as my propagation distance. And so if I write Schrödinger equation here, I h bar temporal derivative of the wave function equal minus h bar squared, or 2m. I'm going to do it in 1D, x squared psi plus b psi. What is the equivalent of k in this equation? The constant that can be big. Or what constant can be small in this one? H bar. H bar typically is very small. So H bar plays the role of 1 over k. And I can do exactly the same game. I would get slightly different equations, but very analogous. And for a Gaussian, I would get exactly the same behavior. In that analogy, these paths, if I ignore the effects of this, I get Newton's equations. I get that these paths that I get here behave like classical particles. But near here, they don't. These paths are associated with an interpretation of quantum mechanics championed by David Bohm, the Bohmian interpretation of quantum mechanics, in which there's a pilot wave hidden behind, and then the particles themselves are like classical particles that bend around because of the influence of this pilot wave. And these are precisely those paths. These paths never cross. And you can see it from the fact that they're normal to wavefronts, so they cannot cross. Crossing would mean that the wavefront is singular. So there's a nice interpretation here, a nice analogy. The flux lines of an optical field are the mathematical analogs of the Bohmian trajectories, while the rays are the analogs of the classical trajectories. Are there questions?
So what's the deviation between the Poynting vector of the full kind, which is E cross, and this one?
Yes. So here I assume a scalar approximation. If you have an E cross B type of field, it's almost the same, but the polarization can create some contribution that is a bit strange. So this is the spin component of the Poynting vector. It's a nice paper, surprisingly recent, by Michael Berry, where he does this nice separation of the Poynting vector of the electromagnetic field into something that is very much like this, and something that is due to the polarization. So, for example, if you have suppose that you have a plane wave that goes like this. So it's going in this direction with this polarization. Another plane wave that's going at 90 degrees with this polarization. The polarizations are orthogonal, so you think they don't interfere. They're equally intense, they're in phase. One alone has a Poynting vector that goes like this. This one alone has a Poynting vector that goes like this. Logic would tell you the total Poynting vector goes like this. If you calculate it, you find that on average over space, that is true, but at each point, the Poynting vector actually oscillates like this as you move on fringes, because there's the spin component of the Poynting vector. This superposition at some points gives you linear polarization. There's no spin component, but at others gives you circular polarization. And there's a component, the Poynting vector goes perpendicular to the ellipse of polarization. So yeah, that's why I use scalars just to make life easier. But there is a part, one would say the main part of the Poynting vector is like this. But there's another component coming from polarization. Okay. So if I say, I'm going to ignore that, I'm away from that focus. Yes?
So these equations account for negative values of vector effects.
What happens if the refractive index has negative values?
Yeah, does the equation account for those?
Yeah, I think so. Well, we have an n squared. I think negative refractive index, as difficult it is to achieve experimentally, it's easier for these equations than imaginary refractive index. So metals and things like that. When this equation gets complex, then you cannot do the separation. This uses the approximation that the medium is transparent, essentially. A medium with purely negative refractive index is transparent, just weird. But there's no absorption, there's no dissipation, because if you think of the e to the I, k, and z, for example, the imaginary part of the refractive index is the one that gives you the exponential decay. So if this is purely negative, well, the phase is going to move in the opposite direction that you think, but you can still use this.
So is that in the Iconal equation that you've written? In the Iconal equation.
Uh-huh.
In the Iconal equation, I noticed that you've written squares of the refractive index.
Yes.
So that means it's somewhere that you haven't discounted the negative value totally.
Yeah. So naturally, actually, this is epsilon. This is the permittivity of the medium. Well, epsilon, depending on your notation, or epsilon over epsilon 0. So that is from the E&M point of view. This is a more fundamental quantity than the refractive index. Refractive index is a square root. Is defined as a square root. So you're going to run into trouble of choosing the appropriate branch at some point or another. And I think a lot of the debate on negative materials and all that is choosing those branches of the square roots is not trivial. Okay. So, what am I doing with time? Well, I should. So if I ignore that term, then I know that I get the race. But this causes this. So these are the flux lines for this not so nice Gaussian beam, but it's not a Gaussian beam, it's an aberrated beam. So you can trace those, and they're tricky to trace. You cannot trace them independently. The beauty of rays is that by ignoring that, they decouple. The ray does not care about a wavefront, does not care about anything. You just trace it. It doesn't care what the neighbors do. While the flux lines do. They have to avoid each other. So that's the second equation. So we have this comparison between the two things. They look a lot like each other here and here, but not here. Want to, before going away from this slide, make a couple more reflections about this. Let's think about this equation here. The iconal, what is the meaning of this functional diagonal, of this function diagonal? Is the iconal equation tells us the interpretation. So this tells me this is equal to n. I'm going to find something that is the optical path length. And the diagonal is that optical path length. If I move from here to here, how much path will the ray have to trace? Knowing that for the ray it's harder to move, in quote unquote, in a high refractive index medium than in free space. So this tells me what is the ratio, infinitesimally, of optical path length to distance, to physical path length. So if I go from here to here, what is the ratio between what the ray feels and the true distance? It's n. So that's the definition of that. So from this we see that this is phi is an optical path length. But it's also a phase e to the I k phi. What this tells me is that this is not complete. Really, I need this plus Laplacian of a divided by k squared a square root. If the curvature of my amplitude is negative, that is if I'm at a maximum or near a maximum at a focal point, this is negative, and this will subtract a little bit. That tells me that the rate of accumulation of phase, of optical path length to physical path length, is a bit slower. I need to move further away to accumulate phase. The wavefronts, therefore, are going to be more separated. So at a focal region, the wavefronts are always more separated, and that's something we have a name for. It's called the GUI phase shift. So the GUI phase shift tells you, near a focal region, the wavefronts are more separated. If I am in an area where the field is decaying exponentially, for example, or has a minimum like this will be positive. And then the phase will advance faster, like here. That we call super oscillations. So what this equation tells you is that really what we learned at school, that the distance between wavefronts is lambda, is almost never true. It's only true for plane waves or spherical waves, essentially for waves where this is 0. Otherwise, it will be either closer, super oscillations, or further away in the focal region. And you can see that it's just geometry here. Because we have this flux lines here, and we draw the normals, because this is flat and this is curved, the spacing here will have to be bigger than here and bigger than here. So the phase will have to advance faster here than it advances here. So this simple equation gives us a lot of physics about things. So flux lines are very useful for understanding these things. I didn't use rays for this at all. Now, why would I care about the rays if the flux lines give us all this insight? So one way to think about this is what I said before. They're easier to trace. They are straight lines. But also they tell us something different and in some ways more meaningful about the field than a flux line. Suppose that I have this beam and I block part of this here. That will create a shadow, and where will I see the shadow past the focus? Will the shadow follow the flux lines or the rays? The rays. So rays tell us more intuition about what happens, how a field propagates at a long distance without having to do all this complicated stuff. In a way, rays tell us more about what we can do to light, what matter can do to light. Flux lines tell us maybe more about what light can do to matter. If I put a tiny little particle here that feels radiation pressure and ignore its inertia and all that, it will move pretty much along the path of a flux line. So they're both useful quantities that are very useful entities that are very similar in many regions, but they differ critically here. So the naive way of thinking of rays is, I have a focus field. Rays are great here, because if I follow with this and I do the full derivation, I find that phi is the phase, and A tells me something about the density of rays. So A squared is equal to density so as the rays, if I solve the questions, I find that as the rays concentrate, or the flux lines, intensity builds up. Intensity is A squared, so the amplitude, I have to take a square root. So it's the square root of the density of rays. When I get to this point here where the rays are crossing, especially these points here where the rays form an envelope, this amplitude, this density of rays is actually infinite. And we can no longer estimate the field with this. This fails completely. So it's like rays are great. Whoa, they don't work. But the magic is, they work again. So somehow, naively speaking, you would say the ray model works up to here. But no, it comes back. And in fact, the rays worked throughout, this way of thinking about the rays is the one that fails here. Yes?
Here you are connecting the amplitude and the phase.
Yeah.
So then it will actually get in line with the temporal coherence also, right? Because the wavefronts are being now, the distance between the wavefronts is being governed by the curvature of phase.
Yeah.
So will it have an impact on the understanding of temporal coherence also?
Yeah, so at the moment I am assuming a purely monochromatic, perfectly coherent field. When you make things partially coherent, it gets a bit trickier. I find that the connection between rays and waves is better in other ways that I will discuss on another day. So for now, let's just assume that the temporal coherence is infinite, and as is the spatial coherence. Oh, it's 40 minutes, and I'm on the first slides. So, so I mentioned these caustics, these envelopes of rays. And this is something that we're familiar with. Probably seen something like this, or inside of your mug with your tea. If it is milky tea, you see that beautiful curve like this. Whoa, I got trapped. I'm going to put this here so I don't get trapped. So those are the envelopes of the ray. So the intensity is indeed very high there, but it's not singular as this simplistic model will tell us. I have a couple of other examples of caustics. So caustics are the focal regions. So some caustics are good. So caustic means comes from the Greek to burn. So there are many words that have that root. Like, well, there's Holocaust. And even the word caustic, you use a caustic substance is a substance that burns your skin. A caustic person or a caustic comment. Other examples of it. So caustic is something that can burn, and as we all have played on with the sun and a magnifier, we know we can burn stuff. And some recent unfortunate consequences were this Dara Hotel in Las Vegas. The architects thought it would be a good idea to make a building that is curved, facing south in Las Vegas, with windows that look like mirrors. And apparently the shape of the caustic to the pool area, and apparently the pool got really, really hot at some times of day. The employees called it the death ray. And a similar one in London, it's called QuIC Talk, and worse because it's curved in two directions. And there were some expensive cars that all plastic parts, they parked in the wrong place, and the plastic parts melted. They have since fixed this building. They put some shades that block this. So caustics happen. So to summarize this part, and then I'll accelerate for the next part. This way of connecting rays and waves, which links very naturally to the iconal equation, works great except caustics. Is there another way to think about how to connect rays and waves? Okay, you're all scientists, physicists, and engineers in particular. What do you do when you're trying to solve a problem and you don't know what to do? What do you try? Let's take a Fourier transform. I mean, Fourier transform never lets us down. Yeah. So what if I look at this in the Fourier domain? So what if I come back here and I say my field is not this, but it is something, I'm going to say some other function b. I'm going to call this a different function omega. I'll drop the arguments for now. B, omega, and then I say e to the, so I parameterize direction, which I call P. I solve parametrically the equations, and then I define a P that is a function of Z, of the translator's variable, and of some parameter that labels which ray I'm talking about. And then I take a Fourier transform of this, e to the I minus this function, the coordinates, for example, and then I need a Jacobi P prime, where prime is derivative with respect to psi. So I say my field is not an amplitude and a phase. Its Fourier transform is an amplitude and a phase. And then I can take this and throw it in there. And initially I was planning to do that, but I think it's going to take too much time. But you can do it. And you get from those equations, from substituting here, you find again the ray, but you don't find them in this form. You actually find them more in this form. So the rays are the same. But their meaning now is different because the contribution of each ray is the value of this integral for each psi, and essentially some amplitude that depends on propagation distance times an exponential like this. And I'm missing a k here. What does this correspond to in free space? A plane wave. So this is another way of linking rays and waves. Now I associate with each ray not an infinitesimal contribution to the light field, but a plane wave that lives everywhere. So I can do that. So what then is this field? I would not say that the amplitude. Yes. Okay. Essentially, each ray does not contribute to the field only where it passes. All rays, like this ray here, would be a plane wave that lives everywhere, and I can add them all, and I get something that works beautifully at the focal regions. So this solves this problem of the focal regions. If I think of a ray not as a local entity, but as a global entity, something that is extended in all space, but very localized in direction, then I get this beautiful focal estimate. And this is the basis of a method called the Richardson-Wolf method for modeling focus fields. Now, let me motivate this, the next part, which is, you might think, okay, we're done. Now we'll solve this problem. We see why the rays are still good here. But there will be another problem. And for that, I'm going to introduce a concept that is phase space. So if I come here, imagine a family of rays like this, and look at what they're doing in here. Each ray has a position and a direction. So if I do it again, I can say that, for example, this ray here has this position, so this position, and then I get this plane where the vertical axis is the direction of the ray. So it has this positive direction, so it's somewhere around here. So you see which ray corresponds to which point on the curve. I do it again. So you see, as I move, these rays go like this. So I can represent the whole set of rays as a curve on this phase space. Position versus direction.
So the weightage of each ray is same? It's just the
Sorry?
The weightage.
Yeah. No, that can vary. So you could paint this with some intensity as it goes. If some rays have more weight, either that or the density of the rays is higher. Yeah. So here, of course, I just show a sample of the rays, but it's a continuum. That's why I have a continuous curve here. Now, before I talked about caustics, do we have a caustic here? This is a caustic, this envelope. What points in the curve does this correspond to? The extremal, so the extremal in X or the extremal in P? The extremal in X. So this vertical bit, right? You were right. What about this extremal in P? Turns out that that is, so that tells you that if I move a little bit, the rays locally will have the same direction. So that would be somewhere around here where the rays are locally parallel. It turns out that that we call a momentum caustic, and one way of connecting waves with as plane waves failed. Like the first one here failed, the position one failed when we have a caustic, the Fourier transform one fails in here. So if you have both, you're in trouble. There's a method called the Maslov method, which tells you, just come with my scissors and chop this into pieces, and use the appropriate method for each part. It's a bit of a pain. Especially that here I just have X and P, but in real life we have, if light is propagating like this, I have X and Y, or X and Y. And I have a PX and a PY. So this space is actually four-dimensional. And this is not a curved surface. And cutting that is not fun. So I'm going to accelerate a little bit and tell you a method that, well, several people have worked on this type of thing, but a method that we proposed many years ago is, I know that the first approach works great if we have no caustics. That the second approach works great if we don't have momentum caustics. The first approach, rays are local. They're perfectly localized in X, but they're everywhere in P. The second one is local in P. It's perfectly localized in direction, but the plane wave lives everywhere. Can we find some balance between the two? You could use Wigner functions, and that's particularly good relating to your previous question for partially coherent light. That is actually really, really good. Another way is I can just put in some localization factor here. I can put a Gaussian, e to the minus k, the spatial coordinate minus capital X, which is the coordinate of the ray, squared divided by 2. And for dimensional reasons, I need to put another constant here, gamma, which tells me is related, doesn't tell me directly, but is related to the width of this Gaussian. So this will make each ray be sort of localized within a region. It's not everywhere. And it have also a finite range of regions in direction. You can substitute this in here, go through the math. And in fact, there are several approaches. Some people have done this where you say, well, this turns out to be like a Gaussian beam. I'm dressing each ray with a Gaussian beam. But then I have to trace this gamma, which is the width of this Gaussian beam. And that's a bit painful. But I think the wave propagation methods in Code 5, for example, use that. The approach we propose is that if you do this and you do the math, you realize that doing things right, this gamma doesn't matter much. You get something that saves you from the caustics. And I'm going to give you a picture of how this works. So by using tools from time frequency analysis, something called the spectrogram or the windowed Fourier transform, I can take the wave field and calculate the window Fourier transform, mod squared. So I move the window, that's the x coordinate, and the Fourier variable is the p coordinate. Ignore this for now. And I see that it follows the curve. What I put here is the spot that one of those Gaussian contributions would represent here. So a Gaussian alone, its time frequency analysis is just a blob like this. If I change that gamma, essentially what I'm doing is changing this, the relative width in X versus the relative width in P. And surprisingly, what we find is the following. Let me stop the thing. So the way to think about this is I have this phase space, x versus p. I have this curve. And suppose that I want to describe the waves here. And I know the race. So the race is this. The analogy that I like is I am a graffiti artist, and I'm going to do something. So first I come with my pencil carefully, and I draw the curve that I want to draw. And that's the race. Then I get my spray can, and I paint this. And that's wave-icing the race. But I have many spray cans, ones whose spot is like this, ones whose spot is like this, and ones whose spot is like this. Notice that these two axes have different units. So the aspect ratio that I choose here is up to me. It's not absolute. So I say this is round, but this is round for some scale. So which one do you think is better for this? Which one of these spots? The circle, because I would be able to resolve this. If I use something that is very, very, very long like this is going to get problematic. I will not be able to resolve this. If I use this one, this is going to get problematic. But if I use something where this, the curvature of this, is determined by the range of curvatures determined by the ray family, then I'm fine. And actually, the result is almost independent of what I choose here. So this is what I'm showing on the figure on the right. I vary this, which is varying that gamma. Look, this is problem in the caustic. This is problem in the momentum caustic. This is actually the intensity recovered. So when I have problem in the caustic, so, whoa, this starts to diverge. I have problem in the direction caustic. There's some features that happen here near the direction caustic. But everywhere in between, the wave field estimate is very robust. So we should think of rays as somewhere between a plane wave and a localized thing. If gamma goes to 0, this goes away, and we go back to the plane wave. That's the limit when the this is this limit, and we have problem here. When gamma goes to infinity, this Gaussian goes to what? To a very sharp Gaussian becomes a Dirac delta, and that removes the integral. And we go back to the initial way that we said, amplitude times e to the I phase. So this interpolates between the two. And by using the appropriate weights, you can get very, very good estimates of the wave field, including all sorts of interference. So we propose this method with my friend and ex-thesis advisor, Greg Forbes. And he came up with the name stable aggregates of flexible elements, because each element is very flexible. You can change its dimensions a lot, and but the aggregate, the sum, is very stable and has a nice acronym, SAFE. And he told me that also because Alonso and Forbes are the two others. Very quickly, just to tie some ends here. But well, before that, do you have questions about this? So this is one of the main messages, that rays are flexible things. And that's why they're so powerful, because they're not the limit, one type of limit of the wave theory. There are many limits of the wave theory. So, yeah.
Just a thought. So if you use weighted transform instead of windowed Fourier, then that could have adjusted the scales automatically.
Yeah. The problem with the Wigner transform is that it's bilinear. And you get all sorts of interference between the, so this curve would not be empty. It would be full of ripples.
What about wavelet?
Wavelet could be, yeah, could be. But this is extremely easy to implement. Diffraction. So if I have my rays, and then they encounter an obstacle, I know that geometrical optics tells me, okay, these rays keep going, these don't. So my phase space curve in this case would be truncated. I would have something here, and it stops there. can I still model diffraction effects? So let's think of a plane wave. So if I have a plane wave, the phase space curve in this case is just a line. And then if I have an obstacle, it stops there. What happens in that case? If I do the window Fourier transform, I see it stops, and there's this halo here, this vertical line. And that actually just comes from taking the window Fourier transform of a step function. But you can interpret that in terms of rays. So this all the rays have the same direction, and then it stops here in some position, and then you have a family of rays all coming from that position in all directions. That is like having this ray here is breaking into a bunch of rays like this. So I can model diffraction if I add a new family of rays that are emanating from the edge. Something like this. And this is the basis of the geometrical theory of diffraction that was proposed by Joe Keller. Yes?
Why only that one point?
It's an approximation, but yeah, the main contributions come from a very small neighborhood from the edge. And you can think about it from Fermat's principle point of view. I have light here, I have an obstacle, and I want to look what happens here. So the shortest path to get me from here is one that gets me to the edge and then here. It's not a regular ray, but it's the shortest path. So
So if you have a grayscale
that's a different thing. That's a different thing, and that's harder. Yeah. Yeah.
The commonness inbuilt should be the lambda scale, right? I mean,
Yeah, exactly. Yeah, yeah.
so that
Which for rays is small. So you can
to make it realistic, one could increase that and then have, I mean, the patch is not necessarily.
yeah. There's
Physicality will differ.
yeah. Turns out that because you're spray canning this, you're sort of putting that blurriness in it already. So the idea is, how do I come up with a spray can technique to mimic this? And that's something that because Joe Keller's theory was from the local point of view, and it worked really well, except the boundary between the shadow and the light. It diverged there. But if we use some appropriate weight of these Gaussian spray canning and derive this particular formula that works really well, then you can model diffraction. So just to come full circle, let's think of our Argo spot in terms of rays. So I have my obstacle. I cannot show you the whole family of rays at the same time because it's too much. So I'm just scanning so you see that all the rays are incident, and I project a shadow that is the shape of the obstacle. But then I need to put by hand my new rays, which are my scatter rays, my diffracted rays. And this, well, first, this is what happened when I dress those rays with the Gaussians. It would look different depending on my gamma, but it would look like that. But then I need to come up with the diffracted rays. And here again, I use a movie to show you the whole set of them. And we can see that all these diffracted rays cross the plane, the axis of the system by this circular symmetry of the obstacle. And I can superpose the contributions of all those and get this contribution to the wave field. If I pull them together, I get this as a ray-based estimate of the field after the obstacle. If I do a rigorous wave computation, I get this. So even sophisticated wave phenomena, such like the Arago spot, rays can tell you about it. Here I use nothing but the rays. I mean, I dress the rays. Yeah.
Along the axis there's a dark spot, right?
It's a bright spot.
No, there's a bright and then a dark and a bright.
No, it stays bright forever.
Oh, I see.
It stays bright forever. Yeah. And in fact, it builds up from 0 up to the intensity of the incident wave.
I see.
So, and this works even I'll show you at the end. Even when this obstacle is very small, you can get to scales that are surprisingly close to the wavelength, and the rays still work. So this idea that rays only work when you have things that are very big compared to the wavelength is you can bring it much closer. So just to also give you an anecdote. I prepared these computations when on the December 1919, January 1920, where we went for our last vacation before lockdown, and it was right before I had to give this talk. So my wife and I took a train, and we were just exploring different towns of France. And I was working on this on Perpignan, which is a town at the border between France and Spain. And then, I think I even left my computer, worked on these plots, went for a walk, and I find the statue to Arago, who was a native of that town. So I thought, okay, this is destiny. Arago is an amazing guy. He was a politician at some point, and he declared the abolition of slavery in the colonies. He did many amazing, remarkable things in politics and in physics. He had 4 brothers, all of which were notable. One was an explorer, one was a writer that worked with Balzac, one was no, 2 of them were explorers. No, 2 were military, and decided to go to Mexico to join the war in Mexico from Spain. I am Mexican, so I didn't know that. And actually, when Mexico became independent, the first head of the Mexican army, independent Mexican army, was his brother. Okay, so with that, I finished some reference of the work with Greg. This was also published in French in a magazine in France. But I hope that I gave you an idea of the subtle difference between rays and the interpretation of rays within the wave theory. And again, all this translates to mechanics. So these ways of thinking of rays are also ways of thinking of classical mechanics within the context of quantum mechanics. Thank you. The single ray? So by phenomena you mean yeah, they follow the same rules. That's what is remarkable about rays. I find that. So there is no specific law. Like all the laws about rays are blurry, but their simplicity always comes out, and that's something that I find fascinating. So for example, if I have this ray, and then I have diffraction. So these are diffracted rays. But then I have lenses and all that. These diffracted rays, I trace them as regular rays. So their laws are the usual ones. And so I don't have to think, oh, this is this type of ray, this is this type of ray. And also if I have an optical system like this, and I trace a ray, this is what this ray will do, no matter of which field it is part of. So if it comes from a point source here, so it's these, or if it comes from a plane wave, it's what the ray does is the same. That is not true for the flux lines. So rays are more subtle, they're less direct than the flux lines, but they're more profound in a way. As someone said about something else, they don't exist, but for sure they're real. Yeah. Yeah. Yeah, exactly. So rays you can interpret in many ways. You can interpret it as local, you can interpret it as very delocalized, or anywhere in between. How they evolve is independent of the interpretation, and that's what I think is very profound. That whether I think of it as a plane wave or as a local contribution, how it evolves is the same. I just need to think of how to interpret them at the end when I have to reconstruct a wave field from the rays. So for example, if I have a long optical system, I don't know, like this, here, I know my final field. If I want to model this with waves, especially if the system is less pretty, I have to really trace the wave field all throughout. If the system is very complicated, we'll have to use some finite differences or something, and that's a lot of computation. If it is piecewise homogeneous, then I can use Fourier tricks, etc. For rays, the ray tracing equations are very simple. I can trace a ray very, very quickly. So I can trace all the rays, get to all the final rays here, and then if I'm interested just in the field here, not before, I just need to reconstruct the field here. So I just trace my rays here to find a wave field. I don't care about this. So to get the field here, I don't need to know the field everywhere. I just need to know the rays, and then wherever I need the field, I reconstruct it there. There was a very nice phrase that I heard from Yuri Kravtsov, a scientist working on this field in Russia. I don't know if it's due to him or whom, but the rays are the bones of the wave flesh. So it is there is the skeleton of the wave field. So what we're doing is forensic work. We find the bones, and we can recover the appearance of the wave field from those bones.
Other question? So I just have one quick one. So when you do have obstacles, when you have the secondary rays,
Yeah.
do they have the same weightage as the primary ones, or
So they have the same what? Sorry.
same weightage as rays?
No. They have a magic weight, which is this function. So the weight decays as 1 over this angular separation as you get away. So they're most heavy near the shadow boundary. So the rays that are this fan of rays near the ray that got there. So this is called the shadow boundary, because it's, if you ignore them, this is the boundary between shadow and light. So near the shadow boundary, they're more important. They get less important as you get away. But here, depending on your gamma, and this weight will depend on gamma, you have a specific behavior, which is some special function. For Keller's geometrical theory of diffraction, these actually diverge, and that was the problem. Yes?
So, sort of a quick question. But for a mirage in a desert,
Aha.
you have n of r is a function of
Yeah.
how far I
Yeah.
How do you bend your rays?
Yes. So mirage was when I started working on this on my thesis, and I was looking for examples that had position and momentum direction caustics. I call them momentum because in quantum mechanics it's momentum. I went to a talk by someone talking about the mirage. I realized that's a perfect example. And in fact, well, by accident, this is very close to what you would see for a mirage. Because with a mirage, what you have is
So the momentum caustic and is not overlapping, is it?
no, they never overlap because one is a vertical segment and one is a horizontal segment. They can be very close. They can be very close. Yeah, so the mirage, if you have a point source here, this is the ground, it's hot, it's a hot day in Campor, and so some rays that come here, that's going to create a gradient index here. The refractive index gets lighter near the ground, and then the rays are going to go like this, and then, well, so there's clearly a caustic here, but it's a bit hard to see, but there's a momentum caustic somewhere very close. I have some very quickly example in a different presentation. so this this is a gradient index waveguide. So it's a refractive index is highest at the center and it decreases quadratically as you go away from the axis. And it turns out that in the paraxial approximation, this is analogous to the harmonic oscillator. It's the equal of the harmonic oscillator problem. And these are sinusoidals, which means that each point on phase space, which is a ray, would just go around and around and around on an ellipse, in a circle. However, if you put in non-paraxial effects, the edge ones go faster. And so if you start with a collimated wave, so all rays have the same direction. They're parallel to the axis, but they have all positions. This gets wrapped up into this. And if you propagate further, it gets wrapped up into this. Caustic, 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 direction caustic, etc. So it's a nightmare for other methods. And these are the estimates of the wave fields using this method compared to the rigorous model calculations. So in each one there are two curves you cannot tell. So the rays can reproduce what the waves do even if you have Gaussian caustics. Yeah.
What I really found profound was you could model the diffraction, like Rayleigh diffraction in cable. It doesn't work if the aperture is at wavelength speed. But your model actually predicts that.
You can get close. So at some point, if it is really, really lambda over 10 or something, it starts being good and it starts being useful. When things are very small, the wave calculations are not so hard. I mean, because the system is small. So I guess the ray model starts being good at the same time that it stops being useful. So here, for example, this is going back to the Arago spot. So this is when the diameter is 10 lambda. So this is wave calculation, ray calculation. When this is lambda, and the radius is half lambda. And it still looks pretty good. This case is almost to do this. So the model convenience before it loses validity in some way, at least for this example. Yes.
In general, rays constitute.
You have to be louder.
In different phenomena, rays become multiple parts. While you adding, it will become like it leads to sometimes divergent series and things like that. Is dressing of the rays will makes that divergence for those series components minimized.
So let me think of it. So what leads to a divergent series? I missed that first part.
I mean that certain phenomena, ray instead of multiple reflections and
With rays, it would mimic the same thing. Yeah. Talk about this. I skipped something at the end of this, which is how you get the ray theory from the first estimate. You have to propose a series for the amplitude, a series in inverse powers of k, and that lets you formally get the ray equations rigorously. That infinite series turns out to diverge sometimes, so that reminds me of what you said.
Okay. Any other? Okay, so if not, let's thank Professor Alonso again.
Thank you.
And I think there are some snacks left. So
Yeah.
please help yourself with the snacks. And again, if you're
Yeah.
still around 5 minutes, you can
Yeah.
discuss.
And just one quick thing. So next time, I'm going to use these ideas, but I'm going to talk about structured light. So beams that have funny properties or interesting properties, I should say. But I like to look at them from the ray and wave point of view. So I wanted to first set up the basis to understand what a ray is, and then we're going to use that.
Yes, the
Okay.
next talk is Thursday and Friday.
Thank you. Thank you.